Now, a final important topic in this first section that we're going to be further talking about in upcoming sections is whether or not a graph is connected. So a graph is said to be connected if, for any two vertices in the graph, there is a path that connects them. So in other words, there is some sort of a way to get from any one vertex to another vertex in the graph. If that's true for any two vertices, the graph is said to be connected. So a graph is said to be disconnected if it's not connected. In that case, sometimes we make the argument that the graph is made up of separate components. So in these graphs down here, this is, if you can kind of look at the organization, it kind of looks like the same graph, except in this one, this graph is connected. So if you pick any two vertices, it is possible to get from any vertex to another vertex through a sequence of adjacent edges. But over here, it's not. So for instance, over here, there is no way to get from A to F. There is no connection for them. So in this case, we could make the argument that when we look at this graph, it is actually made up of separate components, where each component is in itself connected. So this would be an example of one of the components, and this would be another component. Because when we look at the graph, we look at this as an entire kind of like structure. Now, assuming that you have a connected graph, one of the things that we look for in that graph would be a bridge. So, and this is very different than a bridge like in that Koenigsberg bridge problem. In graph theory, we use the language of bridge for any edge that, if it were to be removed from the connected graph, it would cause the graph to be disconnected. So in these two examples, you could perhaps see that I removed edge BF, and that actually caused this entire graph to become then a disconnected graph. So BF, this edge right here, is considered to be a bridge. Okay, if I were to remove it, it causes the graph to be disconnected. Now that's not going to be the only bridge in this problem. So let's try to identify some other bridges. Okay, so this edge right here is going to be a bridge as well. Okay, so if I were to remove that edge, and notice I'm just removing the edge, the vertices would at this point in time remain. If I were to move that edge, now G is no longer connected to the rest of the graph. Okay, so that edge ends up being a bridge. And the same thing is going to go through for this edge down here, from F to H. So these edges right here are also bridges. If those edges were removed, it would cause the graph to become disconnected. Now here's where sometimes it's handy to have a pencil so that you can erase things, but otherwise moving forward you want to maybe get a little bit strong in terms of your visualization skills to be able to visualize if an edge was removed, would it cause the graph to be disconnected. So if you're going to argue that any other edge in this graph is a bridge, so for instance, let's say this edge from A to C. Okay, so if I were to remove that edge and leave all of the other ones, is it still possible for me to get to from any vertex to any other vertex? Yeah, so for instance, it is still possible for me to get from A to H. Okay, or from E to G. So that edge is not a bridge. What about this edge right here from D to E? If I were to move that one, is it still possible to get from instance, G to E? Or H to D? Yeah, it's still possible. So that edge is not a bridge. And you can come through here and you can do that with any of these other edges. Okay, so you'd come with your pencil and you would erase one of the edges, and then you would look at the graph model that you have in front of you at that point in time and ask yourself, is it still possible to get from any vertex to any other vertex through a series of adjacent edges? And if it is still possible, then that graph is still said to be connected, and then that edge then is not a bridge. Okay, so this edge also is not a bridge because that graph is still connected.